The effective conductivity matrix A star is not possible to find in all cases, at least not very easily. We can always find it numerically, but it's also possible to find it explicitly in some special cases, and one such case is the laminate case, which we illustrate here. For example, if we have two different materials laminated together, a white material and a dark material, they are mixed together in proportions V1 and V2, and the conductivity in the white region is denoted lambda 1, and in the dark area lambda 2. So what do we mean by these two volume fractions V1 and V2? Well, the V1 is just the area of the white region divided to the total area. And similarly for the volume fraction V2, it's just the area of the dark part of this laminate structure divided to the total area. So adding these two volume fractions together, we just get 1. In this case, it's possible to show that the effective heat conductivity matrix is given in the following form. The off-diagonal elements are equal to 0, and this lambda 1 1 star is equal to the harmonic mean of the conductivities. This the other diagonal element is just equal to the arithmetic mean of the two conductivities. This implies that the conductivity in the horizontal direction is less than the conductivity in the vertical direction. It's also possible to see this physically, because if the two materials was, for example, metal in this lambda 2 region and an isolating material in the white material, then it's obvious that the conductivity must be less in the horizontal direction compared to the vertical direction. Another example where we can find the effective conductivity matrix explicitly is in case of a chessboard structure. If we in the dark area have conductivity lambda 1 and in the white area lambda 2, we just have that conductivity matrix is given by this formula. Both diagonal elements, lambda 1 1 star and lambda 2 2 star, is just given by the square root of the product of these two conductivities. And the off-diagonal elements in the effective conductivity matrix is just 0. This formula was proven by the Russian mathematician Duchesne in 1972. Let's just repeat that the off-diagonal elements of the effective conductivity matrix is given by this formula is just equal to 0. The simple formula for the chessboard structure motivated other mathematicians to find the effective conductivity matrix for a more general chessboard structure with 4 different conductivities. And two Italian mathematicians, Mottola and Steffe, found a conjecture in 1985. They didn't have a proof for this conjecture, but this conjecture was proven by other mathematicians in 2000. We are also going to talk about something called reiterated homogenization, and in order to get a picture of what this means, just imagine structures in structures. So we will soon show you what we mean by this. Here we have an example of such a structure. We have a chessboard structure inside a chessboard structure. So just recall that the effective conductivity of a chessboard structure was equal to the conductivity of the product of the conductivities in this chessboard structure. So in one area we have this white conductivity, and the white conductivity we can call that lambda 2, and the black conductivity equal to lambda 1. And how are we going to find the effective conductivity for this structure? Well, we now have in fact two conductivities. In the white region it's very easy, it's just equal to lambda 2, and if the other region was just a homogeneous material, then we could just have used the conductivity of that material. But in this case the conductivity is just equal to the effective conductivity of the chessboard structure inside it. So it's equal to the square root of lambda 1 multiplied with lambda 2. So now we have found the effective conductivity of this total structure. So the principle we are using is that we are computing the effective conductivity on the inner level first, and then we can go to the second level and compute the total effective conductivity for the structure. So if we just manipulate a little bit with this mathematical expression, we see that what we get here is just the square root of lambda 2 and the fourth root of lambda 1 multiplied with the fourth root of lambda 2. So just using the simple algorithm for simplifying this expression, we just find that the value we are going to the value for the effective conductivity in both these directions are given by this formula. For the purpose of training your skills concerning reiterated homogenization, consider the following problem. In the first level we have a laminate structure, and the laminate structure is in equal proportions V1 and V2 equal to 1/2, and in one of these materials we have a chessboard structure. So what I suggest that you should do is just to compute the effective conductivities of the total structure. What I mean by this is this lambda 1 star and lambda 2 star. Because of symmetry, the off-diagonal element is equal to 0. We use exactly the same method as before, but try to do it yourself. Go first to the inner level and find the effective conductivity of that level, and continue with the second.